Alright, welcome to a new day. This one's going to be extra fun. We're going to finally build real circuits, virtually though, but we're going to physically make stuff in a virtual environment though. Okay, so let's get started. Let's do some physical computing. I am excited to teach it to you. I do want to say, if you're an engineering major or you've just taken a lot of physics classes, you have probably seen this lecture already, okay? Especially if you're a computer engineering major. But the computer science majors in the class will probably never ever see this information again unless they take a fancier physics class. So this is definitely for the CSCI majors in the house tonight. And if you know all these things already, please help your peers over Discord and all that. And do yell at me if I ever say something wrong, because I am just a lowly computer scientist. I am not well versed in these things. So yeah, where we're going to do our virtual physical computing is on a website called Tinkercad, so please go there, make an account. I'm already logged in, I think. And then there's a little circuits feature that you'll make stuff, and you'll click create. I want to create a circuit, please. Or circuits, I guess. You can bring them together. And it gives you some default name, and I'll call mine like Scratch F24 or something. So yeah, then you can start dragging stuff out, like resistors and LEDs and batteries, and that will actually be the first thing I want to show you. That's the first circuit I'll show you. And you can play around with this. You can like rotate these things with this button. You can also like mirror them, but rotate with either that button or also the R key. All right, and then you can like zoom in. Positive, negative terminals of the battery exist here, and you can start like dragging with your mouse, and that creates little wires that you can eventually hook up to things. Okay, so yeah, just this will be fun, and we will mess with circuits and mess things up and not have to like rebuy LEDs because we blow them up in real life. Okay, so it's gonna be great. We're gonna use Tinkercad for physical circuitry lectures. So yeah, I need to like teach you some electricity rules and things, some physical constants and stuff. So here's your crash course on physical circuits right now. All right, so there is a fun analogy for the things that I want to teach you. So I want to teach you the three pieces kind of every circuit. You've got current flowing through it. We use the I, capital I character, to talk about how much current is flowing through our circuits, and that is measured in amps. That's the standard SI unit for current. There's voltage going through our circuit. We use capital V for that, and volts, naturally, is the standard unit for voltage. And then there's also resistance through our circuit that we use a capital R to talk about, and we use ohms as the unit for resistance, and the symbol for ohms is an omega. Okay, so yeah, there's a cool little water analogy for how these kinds of things like interact with each other, and it makes more sense than it does for electricity. So please go and watch one of these videos. I think the first one's the better one. I cannot show it to you right now because I'm going to put this video on my own YouTube, and if I play somebody else's video, they'll give me like a copyright strike. So go and watch this first video at least, maybe the second one too, and it will show you this cool little water analogy of circuits. All right, so you can think of like voltage, for example, as you got a tank of water sitting up high somewhere, like a water tower at Fresno State or something, and then like it's sitting up there. It is like you got your little tank of water up, sitting up high, and if you have a little pipe, but it's closed off right now, you haven't opened it up yet, water has the potential to want to go through this pipe, right? It will fall through if you were to open it, and that is voltage, that potential for water to fall, electrons to flow. All right, that's kind of the idea. The video will talk about this too, of course. And then, yeah, just like the speed of water moving through your pipe. Speed of water, like water's going to want to move this way, and like the speed of water coming through the pipe at a given spot, or the volume, I guess, of water passing through a point, they say, that's like current. How fast is electricity flowing? How fast is water flowing? Okay, and then if you ever like constrict your pipes, like put a little kink in them or something, then you can imagine like water's going to be flowing like fast here, and then it's going to slow down, and like it will never get any faster. All right, so constriction of your pipes is like resistance. All right, and so for electricity and electronics, this is kind of what our circuitry looks like. You got a positive and a negative end of your battery that you're connecting, and that's going to allow electrons to flow, I guess, in this direction, but we consider current to flow in the opposite direction, thanks to Ben Franklin, I think. We have him to thank for that weird rule. It's kind of backwards, because they didn't know about electrons back then, I guess. And so you got power flowing this way, and current flowing that way, and you got resistance. Those are like little resistors are drawn like this in your circuits. They're little jagged lines, and yeah, that's pretty much the idea. And the battery supplies voltage. All right, so yeah, it's kind of like everything's like a pipe. You got water flowing through a pipe. Electricity is kind of like that. Instead of water, it's electrons, right? So it's like electrons are flowing backwards. Current is flowing this way, let's say. And yeah, that's current. That's like the speed of water, the amount of water passing through a point. If you put a little kink in your water hose, then fewer electrons can pass, right? And so you've got less current flowing. That's a resistance. And then just like if you put a water tower up here, like the potential of electrons wanting to move is your voltage. All right, that's my best example. Going back to water. So it's not the world's most accurate metaphor, but it's good enough for this class. All right, so yeah, you can relate those terms to each other, which is nice. It's called Ohm's law, and apparently the units all cancel out and it works out. Voltage is equal to your current times your resistance. Okay, so that's Ohm's law, and you can also solve for power. So power is another thing we care a lot about, like how much power is flowing through our circuit, and that only requires two of these things, any two actually. So power is measured in watts, and so like you have a 2,000 watt microwave in your house or something, and that's a useful thing to understand. And so the units there are going to be power is equal to either voltage times current, or because you know all these things relate, you can solve for them in terms of the other two as well. So like it could be voltage squared over the resistance, or current squared times the resistance. Those are all different ways to solve for how much power is flowing. All right. But yeah, in computers at least, we work with 5-volt electronics. Like that's the potential difference between ends of our batteries, kind of. That's how much the electrons want to flow. All right, that's their potential. So yeah, we work with tiny voltages inside of computers with our digital electronics. But like your air conditioning unit is going to want more than that. Your washing machine is going to want more than that. Take a physics class if you care to know more. All right, so yeah, let's move on, and I'll talk about some different pieces of our circuit. So like this jagged thing produces resistance, and it's a resistor that does that. So resistors look like this, and they're going to limit both current and voltage in a circuit, because the second you put a kink like this, the water's not going to flow as fast, less current. And then also, like, even if you have a really high water tower, if you have a very small pipe, you shorten your pipe, like you put a kink in it, then obviously it's not going to want to move as fast. Less potential difference too. So voltage and current get reduced. And so like here's a standard problem that I kind of hinted at with this. So let's say that we've got a 9-volt battery, and we'd like to power a red LED, and we do not want to blow up that LED. We want to give it just the right amount of power. All right. So red LEDs, they like to see 2 volts. They like that amount between their positive and negative ends of potential voltage. Potential difference. So that's their voltage, and they want a current to pass through. They're going to draw a current of 20 milliamps. All right, and so milli is the 10 to the minus 3 prefix. All right, so it's 20 times 10 to the minus 3 amps. We always want to get it back because we're about to use this formula, and we have to get everything in the proper units. Okay. So you got to convert back to amps. And so the question now is, all right, how big of a resistor do we need to shove between our power source? Like we got our 9-volt power source coming in. We're going to put a resistor of some amount to limit that 9 volts down to like 2, right? Question, how many ohms? And then we can feed that in to our pretty red LED, all right? That will light up and not blow up, all right? And then we'll have the other side go into the end, to the negative end of the battery. So like we got a bunch of voltage, going to limit it as well as current to baby amounts of voltage down to 2 volts. All right, that's what we would like to do. So how can we do that? How can we drop 7 volts if the LED is going to want to draw 20 milliamps? All right, so we can do V equals IR. So voltage is equal to current times resistance. So we want to drop 7 volts across this resistor. And so we put 7 there. 7 volts is equal to how much current, well, how much resistance times how much current are we going to draw. So it's going to be 20 times 10 to the minus 3 amps, and then multiplied by R. And if you solve for R, that will tell you how big of a resistor you want to put here to limit that current. Or sorry, to limit that, well, I guess current too, to limit that voltage. Okay? So, we got 7 over 20 times 10 to the negative 3. So it looks like 350 exactly. We want a 350 ohm resistor. Bam. All right, so that's how we're going to do that. And let's make this circuit now. So we're going to do it. We're going to eventually use this cool thing called a breadboard, if you haven't seen that yet. We're going to make that LED circuit first without the breadboard and then with one. All right. And so if you go and you drag everything out into your Tinkercad and rotate them as you might want to, you'll see that there's a positive and a negative end of your battery. There's just 2 pieces to a resistor. Resistor can be flipped around as a matter of the orientation of your resistor. But the LED, light emitting diode, the fact that it's a diode, it wants things in a special order. So it's got 2 pieces, and one, like, it's got a curvy part on one end and a straight part on one end. So the straight part is the cathode, the curvy part is the anode, and the anode wants positive. So anode is where the current enters, that's the positive side. You're going to connect that to the positive end of your battery, all right? And this is kind of backwards if you took chemistry, by the way, and you're just seeing this for the first time. Like if you took chemistry, you probably remember like anions and cations, right? And this is backwards because anode is positive. So if this helps you understand the backwardsness, like anions, they're going to want to be attracted to anodes because they're negatively charged, and this is the positive end. So maybe that helps, I don't know. But that's kind of why it's that. And then cathode is where a current is going to want to leave out of your LED or other things. And so that's going to want to be connected to the negative end of your battery because that's where current wants to flow to. Okay? So let's build this circuit just with wires floating out in space right now. And then we'll make it pretty with a breadboard later. So yeah, here's the idea. We would like the positive end of our 9-volt battery to be resisted by a resistor. And then that needs to feed in to the anode of our battery. All right, so positive needs to go to the anode, and if I can rotate this with R, I can feed it in just like, oops, drag to draw a line to make a little thing. So there's the anode, and you can color these because red is usually positive. That means positive, at least for our 9-volt battery. So that's kind of cool. And this resistor, you can configure what kind it needs to be, and that makes the little bands change, because in real life you'd notice which kind of resistor. It's not like nobody's writing 350 ohms on the thing. They're writing these little colored bands, and that tells you how much resistance it is. So this is apparently now a 350 ohm resistor. It looks like that. And then we want this side, the cathode, go into the negative terminal of our battery. And so I'll go to black wires now. And if you just click, and you click around, like I'm going to click, I'll click right here, and you can kind of make a prettier, if you click a few times, you can make a prettier wire that kind of like looks more normal. So, bam, and then we'll eventually feed it into that negative terminal, and negative is black, all right? And so, if you click Start Simulation, you will see a lit up LED. Isn't that beautiful? If you want to change this voltage, like change it to kilo ohms, so it's resisting a lot, you'll see that it gets dimmed. If you change it to very small amounts of voltage, milliohms, you will see that our LED blew up, and we don't like that. So at least we don't have to go and replace it, because this is all virtual. So cool. That's 350 ohms. That's what we need here. So yeah. That is everything I think I wanted to say there. So let's do it with a breadboard now. So this is a cool device called a breadboard that makes it so that your wires just kind of naturally look pretty. And so here is what a breadboard is all about. It's got these holes that you can stick wires into, or also LEDs or resistors, whatever you want. And then some of these holes are like connected to other holes. So this positive thing, this positive rail we call it, they're all connected like this. So the plus part, they're all connected like that. And same with the negative part. They're all connected like that. So if you bring your battery into the plus side, like the positive end of your battery into the plus side, just any of the holes, then this whole rail is powered. Does that make sense? And you do the same thing with the negative end of your battery on the negative side. And if you want to like do the same on this rail, because you know how they're going to be connected, like you can connect this guy to this guy, now you got power flowing on this side, positive. Same with the negative. Well, you can do that too, okay? And then these guys, these individual guys, they're connected in the other direction. So like you got all these dots connected along that rail, all these dots connected, all right? And it doesn't hop over either. Like these guys are not connected to these guys. It's a separate line of dots connected, all right? Separate holes. And so kind of if we want to make our little circuit, here's what we'd probably do. We want to go from power, positive end of our battery to like this rail, and now this whole thing is powered, right? And then we want to connect like, I don't know, a resistor. So like we put a resistor in one hole down from here to here, and now there's positive resisted positive coming through here. And then, I don't know, you can like pass along a wire from here to here. Maybe you can put your LED from here to here, I don't know. And then bring in it to negative over just like that. So it's kind of, see how it's going to connect positive to here, to all of that. Resisted across, now this is all connected. Then over to here and into, eventually the circuit is somehow completed, okay? That's kind of the idea. And so yeah, let's do the same thing that we just did with a breadboard this time. So if I duplicate, you can copy and paste a lot of stuff, copy paste. I'll need all these two things again anyway, but I'll drag a breadboard small out, and what I'll do, I'll copy and paste the resistor, copy and paste the LED, just Control-C, Control-V right now. And then now if you hover over, you can see all the rails and their connectedness, which is helpful. So let's like drag positive to right there. Cool. But positive is red. And then we'll drag negative to the negative part. Bam. And negative is like, it likes to be black. All right. By the way, you could have put this resistor, you could have put it on the negative side. Doesn't matter where the resistor is, as long as it's somewhere between the LED. Doesn't matter, as long as somewhere that current is being resisted, that voltage is being dropped. All right, let's see here. Yeah, so let's do the same thing. So I'd like to take in positive down to a rail or something. So there, positive is red. I'll use a red wire. So now this entire rail is powered, and I'd like to resist that that positive along this resistor. So like positive's coming in to here, resisted across to here, so now I've got, I could hook into here now, any of these, okay? And so I'll hook in this LED and I'll turn it a little bit because I need positive going into the anode. And then, yeah, now we got power coming in this way, flowing out through the cathode down to hopefully negative, and that should be a black wire, right? So can you kind of see positive coming in to here, across the resistor, into the anode, down through the cathode. That's how you look at this breadboard and see it work. And we got the same thing going on. Isn't that nice? So that's pretty cool. So that's a breadboard. That's kind of what it's good for. Whee! So, okay. Now I just want to show you a bunch of these other pieces, okay? Off we go. So here's some more cool examples, and I will show them to you. So we got a few pieces. Got a push button. This is called a push button. This is a slide switch. You can flip it on and off. The button you can just press in and out. And this is called a potentiometer, which is gonna, like, you can turn. Okay. So, let's talk about the first two first. So push button. You push it down, and what happens is this guy gets connected to that guy. All right. You push it down, and like power can flow from here to here. It's an open circuit before that. And also separately, you could like hook two separate things into this push button because it's also going to let these guys be connected if you push it down. So you can have two separate things, two separate LEDs kind of being powered maybe. But yeah, you press it down, press it in, and like then there's a connection getting made here, all right? And then for this slide switch, it's kind of the same idea, but the slide switch can be to the left or to the right. Right now it's to the left, like it's flipped to the left, you can kind of see it. And when it's flipped to the left, this way, then it's going to allow power to flow from this guy to this guy, all right? So it's going to like connect these two pieces, all right? So there's three pieces for a reason, because you can be like, all right, when it's like that, I want to do that kind of thing. Or if it's over here, dotted line, dotted arrow, if you flip it to this direction, then it cuts off this guy, these guys, and it powers this one from here to here. I hope that makes sense. All right, so like you can do two separate things again, which is kind of cool. So that's a push button and a slide switch. Let's just like bring in an LED again and like light it up with if we press the button or flip the switch. I'll do it with a different breadboard. Copy paste. And this time, maybe just for fun, instead of a 9-volt battery, we will use, if you go to all and you scroll down to like power. Oh no, it's not even power. Interesting. And if you go to instruments, there's a power supply. You can also search for it. But a power supply you have more fine-grained control over, like start simulation. You can be like, all right, I want this to be 5 volts. I want it to be 30 volts, and you can choose what's the max amperage that you would like as well. But we can configure this to be just like a 9-volt battery. It's kind of cool like that. So yeah, it's another thing you want to use sometimes. So let's use that to power everything. That's our power source now. That's all. Bring in positive, boop, 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 and negative. And positive should be red. We like to color code things here. And so let's bring in, I guess I'll go back to the basic components. I would like to kind of do the same thing I was doing with all these guys. Maybe I can copy and paste, or no, I'll drag them out again just to show you the idea. So this is here's our push button. That's kind of the idea. We want one of those, a resistor, and an LED, and then we'll place them in the appropriate spots. This should be a 350 ohm resistor. Cool. And so kind of like when you press this down, it's going to like connect this the 1B to the 2B terminal and the 1A to the 2A terminal. Okay, that's what's going to happen. So just for fun, we can power the other side too. Let's do that. It's like bam, positive down there too. Bam, negative down there too. Okay, back to red. So yeah, let's bring in positive to somewhere. Bring in positive to here, and then I'll use this push button to connect positive to this rail. All right. See how if I press it down now, it's going to connect this guy to this guy, or this guy to this guy. It's like it's got two chances to flow over. And then now this rail is powered, and I guess there's only one visible hole to use here. And then I'd like to move that power over to here, maybe. And yeah, let's hook it straight in just to prove to you that you could have done, instead of positive resistor LED negative, you could have done positive LED resistor negative, either order. So yeah, let's go to, positive needs to go into the anode. So bam, we're lighting it up, coming in. If you press it down, we're going, it's jumping across, then we're coming in to the anode, out through the cathode, and then we need to go down to negative, but we want to resist it as well. So we'll go down through the resistor into negative. Isn't that cool? So now if I click start simulation, the light's off, of course, because I haven't pressed the button. So I press the button, you see that it lights up, and it's drawing a little less than 20 milliamps because like all these wires introduce their own resistance. So that's kind of interesting in itself. So, isn't that beautiful? Click on, click off. So this will be a good one to study. Yeah, let's do the same with this slide switch. So like I was saying, depending on which orientation it's on, it's going to like connect these two, the left wire to the middle wire or the right wire to the middle wire. Okay, so we'll do the same thing here. We'll take in positive to somewhere. I don't know. How about here? Oops. Oh, I gotta stop the simulation first. So give me positive, and then give me a slide switch, and then I guess if I want to do it like this, then yeah, I'll just make it so that like this is the side that's on. Okay, so like if it left means on, right means off. Because if it's on, it's going to connect this guy to this guy, and so I want to take power to here, let's say, and then I'll bring in an LED, rotate it because it needs to go to the anode part. So if it's on, like it's connecting these guys to this guy, right, when it's in the left position. So power is flowing from here to, oh, sorry, we need to go hook into like that, anode, and then we can do the same thing with a resistor. Resistor to negative. Okay? So it'll start out on, because like the left means on. It's connecting this guy to this guy. If I switch it to the other side, it's connecting these guys to these guys, which is like cut off the positive, right? Cut off the power. And I highly encourage you to do it the other way, like make it so that the right way powers the LED rather than the left way. It's a good practice thing to do. So yeah, isn't that fun? A fun thing to notice, I guess, I don't know if this is fun for you, but it's fun for me, like, power it, you can see that it's drawing current. There it is, drawing. If you press this, it's drawing double that-ish, because, like, we're powering that LED as well now, too. Isn't that fun? So that's fun to think about for me. Cool. Now let's talk about this potentiometer. It's a little weird, all right? It's got some metal inside in a weird way. It produces variable resistance. It is still a resistor, but it's a cool, weird kind of one. It produces variable resistance. Resistance. That is, I can write that better here. Variable resistance, which is amazing. So kind of the idea is, you've got some fancy electronics in here. It's like some metal, I guess. The more you turn it, like, the more there is resistance between here and here. Like, they're connected, but there will be more resistance as you turn it. That's kind of the idea. And then the other way, these two, just like these two mean one thing, these two are kind of the opposite. If turning it to the right produces bigger resistance between here and here, then turning it to the right produces less resistance from, like, this one to this one. So it's like, it's the opposite on the other side. Like, these guys, if you turn it to the right, they go up in resistance, and then these guys go down in resistance, and vice versa. Okay? So, like, usually just hook into two of the three. Always the middle is included. Okay? So let me show that to you to, like, make our light dim. All right? So we'll get a variable resistance going on here. How much do I want to use here of my potentiometer? Let's say that it can go up to maximum 1,000 ohms or 1 kilo ohm. Let's try that. And these pieces are called terminal 1, wiper, and terminal 2. So there's like a, I don't know why it's called a wiper. You can think of it like, there's some metal going on that kind of looks like a windshield wiper inside that's, like, producing more or less resistance as you turn it. So yeah, let's hook it in. So here it is going in, and let's do I don't know. Let's do it backwards, kind of. Let's take negative in this time. Why not? So negative here, bam, to black, and then I'll connect terminal 1 to wiper. All right, and that should be the one where if I turn it up, it goes up in resistance. Because if I did it backwards, if I did terminal 2 to wiper, that would be, if I turn it up, it goes smaller in resistance. There's a use case for that too, of course, but I think this makes the most sense. So we'll do negative, and so the more you turn it, the more resistance and the less current flows through. From here to here, the less voltage you have as well. So we're hooking it into negative this time for fun. So we got that, and then we've got, let's hook that into an LED. So negative needs to go to the cathode, so that's the right orientation this time. So negative coming in, variably resisted to the cathode, and then just to make sure it never blows up, we'll have our normal amount of a resistor going to positive. Right? So you can read it backwards. Positive's coming in to the anode, resisted cathode over to here, over to the wiper, over to terminal 1, into negative. So it's connected with variable resistance. So yeah, so right now there is no resistance because it's all on the left side. I use these two guys. But if I turn it up, we get more and more resistance. Well, you see that the light gets dimmer. And so you can play around with, like, how much resistance should this have? Maybe if you made it 2,000, it would be even more dim once you got to the right side. But yeah, that's a fun thing to think about. Isn't that cool? So that's that one. And a really cool thing that you can use variable resistance for is, like, you can control an RGB LED with it, which is fun to think about. All right, so there's a cool kind of LED that is could be any color at all by feeding it into giving RGB amounts with power. All right, the current you produce kind of has to, like, produces color as well. So let me show that to you. Let's do a battery this time. Battery. Oops. Go back. There, perfect. Battery, and we've got here's an LED RGB, and then we'll have a couple potentiometers, 3 of them, to control how much red, how much green, how much blue. Isn't that cool? So there's red, cathode, blue, and green, and the cathode, of course, is going to go to negative land. Everything else is going to come from positive. All right. So we'll feed. Kind of the idea is we're going to feed positive in to each of these potentiometers and spit them out into the red part, the blue part, and the green part, and that will correspond to, like, how much red, how much blue, how much green do you want emitted out of this. Isn't that cool? So you can turn up the blue, turn up the red, and make purple or something. So this is going to be disgusting. I'll make it so that, because I did it this way, right? I did terminal 1 in wiper, I turn it to the right, that increased resistance. I want to actually have it increase power to the right, so I'm going to use terminal 2 in wiper, so less resistance when you turn it to the right, if you do it with those two. So yeah, let's go to, this is going to be very disgusting, but I do not care. Alright, so wiper, oops, I'm just gonna do that. It's gonna look ugly, can't really do this in real life, but it's easier this way. And so then I'm gonna have terminal 2 coming out over here and like go into red. This one can go to green, and then this one can go to blue. I know that's ugly, but that's kind of the idea. And yeah, if I click start simulation, right now there's nothing. It's all zeroed out. Let's see, let's do each of these 1,000 ohms still. Are they still 1,000 ohms? No, now they're a little too big. 250 kilo ohms. I guess it doesn't really matter, but let's do, I guess we'll do 1,000 ohms for each. That's what I did in my example in my notes. You can still break your LED this way. You should probably be resisting before this cathode, but I do not care. We will break our virtual LED, it's okay. So yeah, I'll do 1 kilo ohm or 1,000 ohms for each of these. And so if I click start again, so like the power, there's no power coming in, right? Because I'm 0, 0, 0 for everybody. It's like an open circuit, or yeah. So now if I turn up the red, it's going into the red part, you see that it gets red, and then eventually it blows up because I forgot to put like the resistor that you really need here. It's okay, it's fine. So you got some red, and then you can turn up the green. Apparently, a little bit of red, a little bit of green makes kind of orange. Eventually, it gets yellow, and then like the green overpowers it. So there's that, and then yeah, if I turn off that and turn up the blue, kind of gets purple. Turn more red, makes it more pinkish. But yeah, you can play around with this. Just fun colors. In theory, like all of them together in the right amount makes white. But yeah, isn't that fun? So that's kind of a very good use case of these ideas. Okay, so it'd be fun to buy one of these and use it in real life. So yeah, so that's a lot of cool stuff that I showed you. Let me have an example for you to try. All right, so let's use a 7-segment display, and I'd like you to use that to show the number 4. All right, so I'll hook it all up for you, or I'll do the start of it for you at least. Let's use a power supply and 5 volts, and hook that up in this way. So here, where's my power supply? Steal that. It's going to be a 5-volt power supply though. Oh, sorry, I got to stop the simulation first. Power supply, I'll make it up to 5 volts only, and I'll have a breadboard. Oops, have a breadboard, please. Just like that, and we'll hook it up, of course, in the normal way. So positive to positive, negative to negative, and then we need a 7-segment display, which is a fun one. If you scroll down, you'll eventually see it. It's just the kind of thing that's on like your microwave. It has it. If you power it, it's like got all these pieces: A, B, C, all common. DP stands for decimal point. C, D, all these things. They exist, and each of them, if you power them from positive land, from negative land, you have to like it's going to light up one of these little pieces of the digit. Isn't that fun? So we got 5 volts coming in, and we need to hook it up to hook 5 up to the common port up to positive through a 200 ohm resistor. So I will take positive through a 200 ohm resistor. This is apparently what it needs. Positive through a 200 ohm resistor, and feed that into the common port. Boop. So just like that. Something like that, and that's got to be red for positive. And then the rest are going to go to negative, like hook in negative to like try them all out. Try them all out and see if you can get the number 4 displayed. Okay? Everybody else is going to negative. So give that a try. Pause the video. Alright, if you if you try it enough, you'll notice that, okay, I need to do, I think it's this one. G needs to be, that's part of the 4, right? It's part of 4. This one, F. I don't know what the letters correspond to, but we need that one, that one. I think it's, is it A or B? I think it's B. There's definitely an order to it, but I don't remember the order. I'm reading off my answer, honestly. And then it's not the decimal point, but C, I think, is going to do it. And the rest, like, they'll make other numbers, so try to make other ones and see if you can figure out the pattern, because then you can teach me. But that'll do 4, okay? Isn't that fun? Now you can make a microwave, or you can fix your microwave if it ever breaks. So cool. Yeah, that's a good one. And yeah, let's do that just as a fun example. Let's read off a circuit diagram that somebody else made. So remember this one, this is our AND gate. These are transistors. Remember that these things are transistors. And then I'll show you how to read the diagram. These are resistors. These are resistors, and they're supposed to be 10 kiloohms. Ohm resistors. So 10 kiloohms there, 10 kiloohms there. And then this is supposed to be a 70 ohm, not too much, 70 ohm resistor. So this is like, these are limiting a lot, so you don't need much power flowing through into the base of your transistor. Remember the names of these. This is called the base. And as you give a tiny bit of power or current or whatever to the base, that lets a lot of current flow through from this side to this side. It's called the collector up top. Collector to the emitter. So if you're not sending like power to the base, then it's kind of like an open circuit. Nothing's really flowing in this way. But if you send in a little bit of power, just a tiny bit, it'll close it off and let power flow from the connector, or from the collector to the emitter, and then we will see like stuff moving, and that will let you power bigger things. So yeah, apparently we want to use a 5-volt power source, and so here's like the positive end of the battery, and then these little dashes they mean negative. It means ground. It's another word for that. And I do believe that's all that I needed to demonstrate. We're going to use NPN BJT transistors. All right. So see if you can use that. Like, go find one of these in Tinkercad, drag them out, 2 of them, and see if you can build this circuit with like out going to like an LED. So I want you to try it, and then here I will go. I'll start building it myself now, and just like, if you ever notice that like, okay, I get it now, stop the video and try the rest yourself. Okay, it's really, really good practice, I think. So I'm just going to be lazy and not use a breadboard for this one. We're going to use 5 volts of power, because that's what everybody likes to use. So here's 5 volts. Let's bring it down here. 5 volts, and I've got, let's see, I'm going to need a few resistors, so I'll just copy these. And kind of to give power to A and B, like it's either power or no power. So I kind of need switches, like a switch to mean 1 or 0, switch to mean 1 or 0, yeah? That's kind of what we need here, and I'll turn these to try to make it almost like what we need here. So 10 kiloohms for each of those resistors. You see the band colors change. And then we want some transistors now, some NPN BJT transistors. Here's one. Cool. There it is, and we can turn them sideways to kind of have it make it look more like this. So you got the base in the middle, then collector and emitter. Isn't that fun? So we're kind of coming into the base here from power. It's A and B are getting positive. They're from positive. Okay, so here's positive. Let's go to red wires then. Here's kind of what's happening. Positive to, let's say that the right position means power. So bam, into the base. Same from here to this one. Whee! So you got that common to that to another transistor into its base. And so like the AND gate is only going to be powered if there's power coming through from all the way from over here. All right. So yeah, now the goal is to eventually like get power all the way from down to here. So we have to hook into the collector from power itself as well. We're given the full power, not resisting it at all. I don't know the best way to make this pretty there. So it's coming from the top now, I guess, collector. And we connect the emitter of this one to the collector of this one. Cool. I want them to be like in series like this. And then, like if there's power flowing through all the way, we want to like output something and light up something. Like let's light up an LED. So we got to feed it into the anode, right? Because this is going to be positive. Positive into the anode. Should probably be using a resistor here between the cathode, because we'll just bring this down to negative land. But I'm going to be lazy. It's simpler this way. So we'll do that. And then also, in the case, you don't just want like power to be floating around and not like actually connected at all. You want to see in your output, you either want to see like actual power flowing through all the way positive to here, or you want like negative to win out. You want to have this like completed, like the circuit needs to be completed still somehow. All right. So if these guys are still open, there's no power coming into one of their bases, like there's not power flowing down to here, you still want to be connected in some way to like negative land. And so this is what needs to happen. We need to go from negative through a resistor up into the emitter of the second transistor. Don't ask me why, because I'm not an engineer, but the idea is like it produces like a high voltage or low voltage, not like open circuit versus closed circuit kind of thing. You see what's called like a floating value otherwise. All right, so it's supposed to be a 70 ohm resistor. Doesn't have to be much, but if we're not like feeding any power, this is what we want here. Like there's still going to be a baby amount of power coming through, and we just want to like close off that circuit in a normal way down to negative land. Okay. So I'm not qualified enough to tell you why, but ask your favorite engineering friend and they'll tell you. All right. So this is 0, 0 right now. 0 ANDed with 0. 1 ANDed with 0. 0 ANDed with 1. There's still nothing. But 1 ANDed with 1. Power flows through, and we almost blew up our LED. So we should probably have a resistor from here to here. But who cares? All right. Good enough. Good enough for our purposes. Isn't that fun? I think that's fun. So yeah, we just made an AND gate ourselves. We followed this. Okay. Yeah, just a couple more things to show you. I want to talk about DC versus AC. So DC, in addition to being a band name, right? You've got DC stands for direct current, and so it's like you've got like a constant amount of positive voltage. That's what you're getting. That's direct current. Electrons are moving in one direction at a constant voltage. That's what DC is all about. And that's what most of our digital electronics require these days. Like electrons are flowing in this way and this way only by a constant amount of voltage, all right? Pulling them across. So most of our electronics need this. Everything that you have these days, like your laptop, for example, there's always a little block somewhere before the laptop power comes into your actual laptop. Like all of your chargers have little rectifiers that convert AC, which is the other kind of power, into DC. Because AC is what's coming through your wall socket. That's what's easier to like transmit along long distances through wires, but not what our electronics want. So yeah, AC stands for alternating current. It's when you've got you're going up and down, like you're alternating between positive and negative voltages with like a sine wave. All right, so that means like if you look inside of a cross section of a wire, your electrons, they're not like moving in one direction. They're like oscillating. They're going back and forth. They're being pushed and pulled like waves in the ocean almost. So AC stands for alternating current. It's like going up and down. It's like a little sine wave. So you got positive voltage, positive voltage, negative voltage. And in the US at least, we have 60 hertz sine waves with 120 volts. All right. And so like you've got positive 120 on this edge of the sine wave, negative 120 volts on this edge of the sine wave. And it's just like oscillating back and forth 60 times a second. That's what is going on in the US at least, all right? And most of North America. Or, sorry, I think all of North America is like this, but like Europe is something different. So, yeah, let me show this to you, like the difference. And, yeah, we'll use instead of a power supply, we'll use what's called a function generator, which is like a cooler power supply that can make alternating current happen. And we'll use just like a normal light bulb. So here, let's scroll down and drag those guys out. So, where do I want to put that? Yeah, so instead of just like a power supply, you go to like all again. If you scroll all the way down, where is it? instruments. So if a power supply is a function generator, which is interesting. Cool little name, and you can see like it can generate different kinds of wave forms, different kinds of power coming out. So positive and negative, and we'll feed these guys into, let's do just a normal, like, old school, not an LED, but like an actual light bulb, all right? So the way the light bulbs work, by the way, there's no, like, one needs to be positive, one needs to be negative. No, it just needs power flowing through, because, like, the power flowing through will heat up this little filament thing, and that will produce light. It's the old school way of doing things. So this function generator, we can change its frequency, like make it 120 volts, just like our normal wall sockets are. Feed in positive, feed in negative to this light bulb, and then we'll slow it down. I'll show you. All right. So start simulation. You'll see that even though it's 120 hertz, like it's going off, or sorry, it's supposed to be 60 hertz, isn't it? 60 hertz. Boop. You spin it, like it's different. If you go to 60 hertz, for example, that's like exactly what our wall sockets are all about. You'll see that the light remains lit, all right? And that's because like the electrons are moving back and forward so fast still that the filament stays heated up, and so the light's still being emitted. But if you slow it down, sorry, I want this one for sine wave. If you slow it down to like 1 hertz or something, then you can actually watch it change, because it's like it's being 0 for a second, right? Electrons are moving really fast for a split second, like in between. It's 0 volts. It's not there's no power at all. Does that make sense? That's kind of interesting. So yeah, you slow it down enough, then you can see the light like go on and off. Like, what is it? It's gonna be just once a second, I guess, because it's 1 hertz. And that's kind of interesting, and that's AC power, all right? DC power is everything else we've been doing. All right, this has been emitting DC power. Direct current, always positive 9 volts, always positive 5 volts. All right. So, yeah, I think the last thing that I want to show you, there's not really anything, it's not on Tinkercad at least, but you can imagine like you have very powerful things, very powerful electronics. If you're an engineer, like this is going to be important to you one day. Like we're using 5-volt digital electronics all over the place. You're not really using 5 volts out in your air conditioner, for example, right? But you're using 5 volts to control your air conditioner, aren't you? That control panel is not going to power your giant box, right? You might need 100 or 240 volts or something even. You might need to like double up. So the way to get 5 volts electronics to power some giant like 240 volt thing is use what's called a relay, right? It's a little box. Think of it like a box. It's essentially like a fancy transistor. It's a heavy-duty transistor, right? It uses, just like a normal transistor would, a relay, it uses a little tiny bit of power, like a low power input, to control, like you send in a 0, for example, it controls a high power output kind of thing. Like you got high power coming in, and if you feed it in a 0, like the circuit's open and like it's coming out to your AC or to like the little fan inside of your house or whatever, and so that's kind of what's happening. But if you send in like a 1, higher voltage at least, more power, that will cause this circuit to become shut, and a lot of power gets to flow through down here. But you're still using tiny voltages up here. So it's just an electronic switch, like a heavy-duty transistor. It's gonna like lead to your AC turning on, for example. And I mean AC as in air conditioning, not alternating current this time. So you can actually hear relays happening. They're physical devices. And so like, you know that when your AC turns on, you can hear a click? That's the relay. It's turning on the high power from the low power box noticing that like, oh yeah, it needs to get colder inside or whatever. So that's fun stuff you can look up if you want to know more about it. I am of course not an expert, but I can help you search at least for an answer. But I think that's all that I wanted to show you today in terms of physical computing, and I believe that's all that I want to do for the lecture. Yeah, that's it for the day, and I hope you found that interesting and fun. Definitely try it all yourself on Tinkercad, and I will see you next time.